So by now you should be done with Chapter 5 homework. If that's not true, you should probably come see me. You should be definitely into Chapter 6, starting that out. Okay. Yes? On the 22nd. It's on the homework sheet. You guys, everybody okay? You guys doing all right? Nobody can shut a room down like a math teacher, I tell you. Okay. So there's no questions from homework. Yes, okay. Okay, where are we at? The quiz? Okay. What happened, sir? So here's where you expect things to fall. This is the max and min usual values. There's 3 unusual. Oh, somebody's lined up. Oh. Okay. So, I'll remind you about a couple things. In a minute here. So no questions, no other questions from homework stuff? Okay. So just to remind you guys, have any of you guys tried out the Math Study Center for help with statistics? Anybody? Has anybody done that? How is it? Good, okay. Sometimes you can get a tutor that might not know their statistics as well.
I mean,
maybe it's been a while since they got
Math
to.
Center is better than the tutor upstairs.
Oh, the downstairs is better than the upstairs?
Yeah.
Oh, wow. That's the first time I've heard that.
Yeah.
Normally I hear that the upstairs is a little better.
No, the upstairs only 2 or 1 of them. He knows everything.
Oh, I see, yeah. Kim.
Kim.
Yeah. He's been there forever.
Yeah.
Okay. So real quick, I don't know if you expect to get everything you need for a course while you're sitting in the class. That's an insane thought, right? This is why we have homework. This is why we have support stuff. This is why I have office hours. This is why you should go find a study guide if you need it. Go to Barnes & Noble. Don't even have to buy it. Just pick it, go sit in their little cafe, do some stuff, and then put it back and then leave, right? You can even bring your own little coffee and drink so you can, I understand money in college. You can come see me, you can go see tutors, but it's you. You have to go do that, right? If you're not doing much homework and you think you're going to learn everything in the class, you should know by now that's not working, right? That's because it's not the way it works. Okay, so I think we finished chapter 6. We can do another example before we get into chapter 7. Let's see. Yeah, cool. Let's look up this chart. So if I have a normal distribution, I have a normal distribution. That means I can draw this bell shape. Right? And there's that thing about that's a paranormal distribution. And I tell you the mean is 11 and the standard deviation is 2.39, let's say. And then I want to know what's the probability that I get something that's higher than 16. Okay. This is a standard classic z-score problem. You need to do these enough, which is why I assigned as much homework as they did in these sections, so that this just becomes second nature. Because what we're going to start to do is we're going to start to tweak things a bit, right? Why am I able to do this problem? What is the main thing up there that tells me I can do this problem? True, but I'm always going to have that. What is it that tells me I can do probabilities with this? Because it is a... No. If I didn't know that, I'd have to... If it was uniform, I could do it. If it's normal, I got a chart, I could do it. If it's a triangle, like the other day, you could sit there and tease out the math behind it, still find the areas. Are you guys... You have to have a way to find the areas. That's the huge thing. Are you guys semi with me? So if it's a big box, that kicks ass. Any sub area is going to be a little rectangle. Bam! Rectangle, best area formula ever. Triangle, a little sucky, right? Because if I had a triangular and I want to know between here and here, anybody know what shape that is? That shaded area? Trapezoid. Ooh, there's an area for a trapezoid. You can look it up. You can still do it, right? And normal curves, I can't do it using geometrical formulas because there is no geometrical formula that says curve each side. But I have this whole chart that calculus people made a computer make, and I'm like, thank you, calculus people. And I just look up the areas. Is everybody with me? I see you continue to make this area is probability from the visual, right? So probably x is greater than 16. This is why I ask you to do what I ask you to do. What goes in the middle? 11. Where's 16? Over here. Please do, God. Have people put it in. Just like throw it in there. So over here somewhere. Where's the area that I want?
To the right.
Yep. All right. Why do I make you do this? Several reasons. Number one, so I can see that you understand what I've given you. Number two, so you can remember it is the area that's the answer. So what I know is going to be true. Is it going to be a big answer or a small answer? Small. So if I get 0.8, I'm wrong. I know that. Unless I drew my picture wrong, which really sucks. So just don't draw your picture wrong. Okay. So what are the steps involved here? What do I do?
We find the area to the left.
Well, how do I do that? That's the last thing, is to find the area. What's the first step with what I know?
So we find the z-score.
Yeah, because what's that chart require me to know to use it? So look up probabilities. I need to know the z-score. It's the z-score chart. So I make a z-score out of what?
The x, the value.
Out of everything, to be honest. What's the z-score for this guy? 0. What's the z-score for 16?
16 minus 11.
Yeah, 16 minus the mean.
11.
11. Divided by the standard deviation.
2.39.
2.39. That is a measure of how far away that is relative to the data. So that's why it's connected to how much area is left outside of it. So I don't know, what do you get for that?
2.09. 2.09.
2.09, okay. So I put up here 2.09. Now hopefully everybody has a z-score chart because I ran out. Pretty sure. I don't think I have any more. I don't even have one for myself. That sucks. So,
0.9817.
yeah, let me borrow somebody's. Electrical sound up there. All right. Oh. All right. So just remind you how to use this chart in a minute. So I desperately want you guys. You start to lose a little bit of connection with things when you have to go to a chart. But that chart is somebody already calculated all the areas for us. That's all that is. It's like somebody took a big box and calculated all the areas of the rectangles for me. I'm like, I didn't need you to do that, but thanks. This one I need some freaking help on. I don't know the area formula for that. Yes?
When we take our quiz, will we have this chart?
Yes. So when you guys, I didn't say this when I passed this out, and I always forget to say this. If you did write notes on this, I will bring blank copies so you can use a blank copy. You're going to be either turning them in or just showing it to me when you turn in your quiz, because you're not allowed to have notes that other people don't, right? It only makes sense. So hopefully, if you didn't write on it, you can just bring your own. And when you turn your quiz in, you just show me both sides of the z-score chart and head out. I don't like to collect them because you need them for homework, right? So if I look this up, 2.09. Hopefully everybody gets how this little chart works. Oh, look at past Jeff. Help me out. That's you. All right. 2.09. So 2.09. Yeah, 0.9817. So these are the second decimal place, which explains why we always round z-scores to two places. Now I've totally forgotten. What did we just say? 0.9817? 9817?
Yeah.
And is that the answer?
No.
Hell no.
1.
Yeah.
It's like, I'm not going to help you, John. You're a math boy. Do it. I just remind you guys, it's a slight little tiny shortcut. If you look up negative 2.09, you get 0.0183 because of the symmetry. The area in this tail is the same as the area in that tail. Doesn't really matter. It's not a huge shortcut, so who cares if you don't know it. I like it. Okay. So that's the standard z-score problem. Not difficult, right? Okay. I say that not to make you feel bad if it is. I say that to let you know it shouldn't be. So if it is, you should come see me or somebody. What we're going to get into today is our first little tweak of this. Something that doesn't really ring true with what we've done so far is, what do we normally do in statistics when we want to study something? We go and we take sample. That isn't really in this yet. So what we're doing today is we're going to bring in, if I take a sample and ask a question about that sample, how does that affect the math? So far we've been talking about individuals. If I pick one person or one thing, what's the probability it's longer than this or older than this or whatever. So what happens if I take samples? So I gave you, we're going to look at this in a minute, so make sure you have this. It's on the other side of that group worksheet we did last time. The most colorful little handout I've ever done. Yeah, good job, Jeff. 2 colors. Yay! So don't necessarily try to make much sense of this yet. Okay? I'm going to give I'm going to try to get you to understand the idea behind what happens. That paper is a very specific, concrete example of it happening. But it's more important first to understand why something like this is going to happen. So, let's say I go to alternate universe Florida. I don't know if I've used this yet. And I ask people how old they are. And what is Florida like? I used to live in Florida when I was really young, right? And it doesn't go up as sinkhole. That's all we have for terrain changes, sinkholes. But what do you think the population is like? There's a lot of younger people, and there's a lot of much older people that go to retire because it's hot and they like hot. So we have a lot of younger people and a lot of older people. So this is alternate reality Florida because I'm saying there's nobody in there. Just for example, right? You guys with me? So there's a lot of people from like 0, just born, up to 20 or something, let's say. And then there's people from, well, we better let them drink. All right. And then there's people from 40 up to 100 or something, right? And I'm saying there's like nobody in the middle. Okay. How you guys doing? So far, so good? So this is me. How did I make this picture? I just made it like, but pretend like this is real. What would I do to make this picture? I go to somebody, how old are you? You tell me, and I plot it. I say, how old are you? I plot it. And then boom, 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 they stack up like this. Is everybody with me? So each of these dots represents one person. I like it. Is this normal? Is this normally distributed? Oh, hell no, right? The mean is like, let's say the mean is right here. Kind of makes sense. Okay, I like it. All right, everybody good? And then standard deviation, I don't know, something like this. Okay. Now, alternate reality God, or whatever deity you like best, reaches down and says, I'm going to, all right. Earlier this semester, there was something called Chev's Theorem. I can't remember if the book talks about that. I was about to launch into my discussion of Chevy, because it's the other thing I use this for. Let me back up for a second. What if I, instead of taking one person, no alternate reality God, let's not talk about the deities, what they would do. This is for one person, right? What if I took 10 people at a time instead? So what I mean is, instead of saying, how old are you, and plotting it, I say, how old are you, 10 people? What's your average age? Talk amongst yourselves and tell me, right? What do you think is going to change about the picture? So I'm going to make a dot for the average of a group of 10 people. What's the most likely average age of a group of 10 people? Another way to say that is, if you had a group of 10 people, what would you expect their average to be? What's the expected value of their average age? What do you think? So if I told you the average age in here right now is 20, and I take 10 people, what do you expect their average age to be? Close to 20. Are you guys with me? That's why we call the average the expected value. That's what I expect as an average. I like it. It would be really weird if I randomly took a group of people, 10 people, from a room that had an average age of 20 and their average age was 80. Would that not be strange? Hell yes. You're like, are you sure you picked from that room? What's going on? If I randomly select people, their average should be close to the real average. I like it. So the most likely thing that's going to happen is a mixture of people. If I take 10 people, I'm going to get a mix. So when I draw this picture, if that's the most likely thing to happen, where should be the highest peak? On the mean. So I talk to a group of 10 people, I take their average, I plot it. I talk to another group of 10 people, I plot their average, I plot their average, I plot the next 10, I plot the next 10, I plot the next 10. And then I get this. Something that's probably going to look like a little bit like this. That should really be lined up at all. I really want this to make sense. The most likely thing to happen is to get a mix of young and old. If you randomly select people, you shouldn't get nothing but newborns, right? You should get a mixture. Is it possible to get nothing but newborns? Yes, it's possible. But how likely? Not very likely. What's the most likely thing? Something around the mean. Is this looking now? It's not normal, but is it more normal than this? Yes. Shit, yes. Right. Now, what are these little peaks? Because the next most likely thing is a bunch of people from right there. Or right there, right? Now watch, this is cool. This is not a proof, but this is just me explaining why the idea makes sense. What if I took 50 people? I'll just cut to the chase. Here's what this would end up looking like. In fact, around 30 is where it starts to really look like this. If I take 50 people randomly, how likely is it that I get 50 99-year-olds? Very unlikely. That's why it's so freaking small down here. What is the most likely thing to happen? With 50 people, their average age should be the freaking average. It really just should be, with very little wobble. So there's going to be very little times I pick nothing but 50 newborns. Randomly pick you. I'm ready to pick you. No. I'm gonna definitely get a mixture. Are you guys getting the idea? Whatever the standard deviation was, what's true now? Is it bigger or smaller? Does this get further away from its average than that does? Hell yeah. So that guy's standard deviation is going to be smaller, much smaller. It kind of runs to the middle. I'm going to introduce this this notation. You ready? Sigma is for one person. It's the standard deviation of individual people or things. When I take a sample, the average of all the sample averages is going to be the same. Let me do this again. So if the average age in here is 20, and how do I calculate that? I take each person's age, add them up, divide by how many there are. If instead I took two people's ages, calculated the average, and then averaged all of those up. Let me say this again. If instead of taking one person, I took two, took their average, two, took their average, and then averaged those averages, will it be different from 20? Hell no. Still the same people, right? Let me say this again. So if I take each person, calculate an average age, you get 20. Why would it change if I take two at a time? It's still the same people. Why would the average only get bigger or smaller? Did somebody age a lot in the meantime? That took you 10 years, Jeff. Oh, shit. So, for example, if I have 1, 2, 3, what's the average?
2 of 10.
Okay, now, this is a little example of this colorful paper. Let's take all possible samples of size 2. So I could pick 1, 1, 1, 2, 1, 3. I could pick 1, gather 1, 2, 1, 2, 2, 2, 3. I could pick 3, 1, 3, 2, 3, 3. Is that cool? And this is with replacement. I don't want the probabilities all changing. All right, now stay with me. So this is 2 at a time. 1 at a time, the average is 5. 6 divided by 3 is 2. What's this guy's average? This guy's average is 1. What's this guy's average? 1.5.
2.
2.
1.5. 2. 2.5. 2.
It's trying to be a 3.
2.
2.5.
And
3.
3.
Now, if you take, somebody help me out. Let's do this real quick. 3 plus 5 plus 6. Does everybody see what I'm doing?
Yeah.
Take the averages, average them up. So average the averages. The average of the averages should be the frickin' average. Holy shit. That should be like average. Right? Let's see if it works. 3 plus 5 plus 6 plus 3 plus 1. Divided by 1.79. What do I get? 8, 9, 12, 18 divided by 9 is?
2.
Holy shit. 2. I mean, so please let that make sense. Just instead of taking 1, I take 2 people at a time and average the averages of those 2 people everywhere. I'm going to get the same average. Am I not? I have to. It's the same people. No. All right. Sure. All right. Well, there's a concrete example of it happening. The average is 2. If I take 2 people at a time or 2 things at a time and average the averages, why in the hell would it be any different from the actual average? Okay. All right. I'm not sure how else to say that. Okay. We'll look at this paper. It's got a little bit more bigger of a problem on it. So here, what is this a picture of? This is a picture of individuals. This is a picture of sample means. I took a sample, had them calculate their average, put it up here. So we call this the sampling distribution of sample means. Oh my God, it's a long ass name. Here, this is individuals. There, that's groups. Period. Every dot on this represents a group of 50. Every dot on this represents a person. That's why this picture can look like anything. But if I average stuff out, it should look a lot better, a lot smoother. It actually comes out more normal. Okay, so what we're working with is the mean of the means. Oh, shit. Little subscripts mean specific thing. This is the mean of the means. And this is the standard deviation of the means. The mean of the means stays the same. What did you guys tell me about the standard deviation? It becomes smaller. And here's the actual formula. It's going to be divided by the square root of n. Do you see how this was more spread out than that? The bigger the sample you take. In fact, if you took the entire state of Florida and calculated the average, of course it's going to be exactly equal to the average, right? So if your sample size is everybody, you suddenly just get, so the bigger n gets, the smaller the standard deviation gets. This is a 0 standard deviation. It's kind of like if n was infinity. Okay. Now what's really funny is this is the idea behind what happens. The only thing that really changes in the work is instead of using this, I have to use this when I'm talking about a group instead of individuals. So in the work, it's a small change. So let's try a problem. Well, actually, before I do it, let me show you this. And then we'll do a concrete problem. So this is my attempt at showing you a concrete example of what happens theoretically, but this isn't in theory, this is just doing it. So I sort of started to do that earlier. The minute you get more than 3 things, the bigger your sample gets. So this first picture is me just plotting the individual things that could happen. You could get a 1, a 2, or 3, or 4. And they all have a probability of 0.25 because there's 1 out of 4 for each. So it starts off uniform. It starts off kind of nice, right? R started off pretty gross. So now I take samples of size 2. I take every possible sample of size 2, and I've listed them. Right, so sort of like we did earlier. If I reach into this hat, I pull out a 1 and then a 1, well, its average value is 1. That's amazing. So I've done all the averages of all the different possible groups of 2. So that's now my new data. These means are my new data. If you calculate the mean of this new data, you still get 2.5, the same way it was before. Right, the average of 1, 2, 3, 4 is 2.5. If you average up all these things in yellow, if you just average them up, and if you don't trust me, you can do it, you get 2.5. Can you guys see it, though? Isn't it 1, 1.5, 2, 2.5, 3, 3.5, 4? It's symmetric with 2.5 in the middle. So, of course, the mean is 2.5. Look at the picture, though. How many 2.5s are there? And how many 2s and 3s? There's 3 each, right? So look at the picture now compared to what it was. If I plot the groups of size 2 that have an average of 1, that have an average of 1.5, and so forth, does it look more normal? It already looks very normal, right? Why does it already do it after just 2, where mine didn't look good after 10? Because it already started off nice. It doesn't take that big of a sample to make it look normal. It already started off nice. Okay, if you did calculate the standard deviation of these, you would get 0.791, and that's actually the old standard deviation divided by the square root of 2, which was the sample size. That's that formula I put up there. All right, so before I completely lose you, and some of you guys are like, it's too late. Let's do a concrete example of a problem you would actually have to do. Everything I've done up here is the theory behind what happens. Let's see what this shit happens, right? Go back here. Cooperate. Okay. All right. So let's say men's heights are normally distributed. 69, sigma equal to 2.8, I think. So I like to do this. I like to do a part A, which is chapter 6 stuff. By the way, this is chapter 7. And part B, that's chapter 7. When do I know to do this weird shit? When do I know to do this, change the standard deviation? Well, what's n mean? What's n?
The sample.
Sample size. So get, and look, sigma x bar, right? So I know to do that weird shit when I take a sample and I ask a question about the sample mean. That's the trigger that tells me to do this. So in this first question, watch. First question. Pick one man. What's the probability that he's taller than 70 inches? The funny thing is, the formula works even if n is 1, standard deviation stays the same. So do I need the standard deviation for a group of people for this problem?
No.
No, because I'm only picking one person. So this is just straight up normal z-score, right? I know it's normal, so I can draw the picture. Right in the middle goes 69. 70 is over here somewhere. Greater than is up there. I like it. Keep going. Finish that out real quick. So this is nothing new yet. Part B is going to be the new thing. Anybody else like their quiz back yet? Quiz. All right, guys. So this will be, how do you set this formula here?
70 minus 69, 2.8.
Yeah. So our data point that we're interested in minus the mean divided by how big the standard deviation is. And whatever that is.
36. 0.36.
Yeah, sounds about right.
That's the area of
How are we doing there? Anybody?
Yeah.
All right. Let me look that up. Don't say anything out loud yet. Try to find that on the z-score chart. The minute you look up a z-score on the chart, where do you put what you get? Where do you put the result? Where do you put it? I don't know. Where do you put it? What's the chart tell you? Areas that are
to the left.
below.
Yeah.
All right, so when you look up 0.36, what do you guys get? 6406?
Yeah.
Okay. If you cannot find that, if you have no idea where that number came from, right now is a really good time to ask. Or just accept your fate. All right. And is that the answer to my question?
No.
No. I need this side, right? I shaded it for myself to be really nice. I'm like, thanks, past self. That's really good of you. So what's this side going to be?
1 minus
Yeah, 1 minus that.
3, 5, 9.
Coolness. All right, so that's old news. That is old news. And you're all like, for you it is. I just learned this shit. All right, but that's not today's stuff, right? You've got to get into chapter 6 immediately. Because there's a quiz on Monday. So part B is going to say this. Part B says, for your round we select, what you got, Jeff? 23 men. Find the probability that X bar is greater than 7. So, When do I change the standard deviation? When can I not use the given individual standard deviation? When I take a sample and they ask a question about the sample mean. Did both of those things happen? Yes. They took a sample and they're asking about the probability that the sample mean, the average height of those 23 men, they want to know what's probably is greater than 70. Should it be bigger or smaller than this? Oh shit, you're like, how would I know, Jeff? But think about it. If you take a group of 23 men, their average should be close to the mean. So the probability that they're greater than 70 should be small. So what's the probability I go out? Is it likely I can go out and just randomly select a dude and they're 6'9"? It's not impossible. What about if I go randomly select 23 people and their average height is 6'9"? Which one's less likely? The second one is freaking less likely. If I did that, I'd be like, where in the shit am I? Where am I? Some other country probably, where the men's heights is actually hot. Now, so here, it doesn't really matter that you make the picture skinnier. What goes in the middle? Am I green? You're not working. Come here, please. What goes in the middle? The mean, which is still 69. So when I take a group of people, the average of all the groups will still be the same as it used to be. But what changes?
The standard deviation.
Yeah, I cannot use this. Why can I not use this? What is this for? Individuals. What do I got? Freaking group of people. Do you see? I'm trying to show you. When do I know to do this? It's the hardest part of math. Yeah, I get that shit. When do I do it? I totally understand that frustration. So here's the reason. Because I got a group of people, I'm looking at their mean, so I need the new standard deviation, what I call the new standard deviation. It's really the standard deviation for groups of size 23. It's quicker just to say the new one. So that's the old one divided by the square root of n. So how do I set this up? What goes on top?
2.8.
2.8
Yeah.
divided by the square root?
20.
23. That's the sample size. That's what n always is. And that's like 0.6, I think so.
0.584.
584. I like that. You're like, yeah, Jeff. Math boy, I guess that's all right, 0.6. Did it in my head.
Well, you wanted 3 decimal.
No, yeah. But please, dear God, don't give me that much. I can't calculate it 3 places in my head. 0.6 is pretty good in my head. So 70 is still, here. I still want this area. But now when I go to, so that's the only change. All the work I'm going to do is the same. Instead of using 2.8 here, I'm going to use 0.584. So a really freaky ass concept. But what does it do to the work? Not much. It really is just you knowing when to use this. That's what it boils down to. This is really the only change. So now what do? I make a z-score. How do I make a z-score? My data point minus the middle divided by the standard deviation. It's going to be 1.86. No, I don't know. What is it?
1.71.
Shoot. I was sort of close. 1.71? Okay. And then you look that up. We predicted this would be smaller percentage. Because when I take a sample, it should become like this. There should be a lot more in here. There should be less out there. So it should be less than 0.3594. And what do you guys get? Well, give it back. When you look up 1.71, you get, what do you get on this side? 9?
564.
564?
Yeah.
So then the actual answer is going to be 10436. 4% chance versus earlier it was a 36% chance. Since everybody rushes to the middle, there's less stuff left outside. That's exactly what this result means. Okay. So, one last thing to really nail down, and then I'm going to give you guys amazingly enough, a little worksheet to work on. So what we're working with here is called the central limit theorem. What's the center of the data that we've accepted? Center of the data we've accepted is the mean. So in the limit that my sample size goes to infinity, everything's going to go towards the middle, the center. Central limit theorem. From here on out, affectionately known as the CLT. Chicken, lettuce, tomato. So it says a couple things. It says the larger n gets, the more normal the x bars get. So when I graph the means for my samples, the bigger the sample sizes get, the more normal, like up there, the more normal the results become. Here's the magic number. If n is greater than 30, then the x bars are normal enough. Normal enough. Normal enough for what, Jeff? To use the chart. So I don't care what the distribution looks like at first. If they have a sample size of more than 30, I know it's going to be normal enough to do probability work. Why over here? Real quick, that was 23. That's less than 30. Why do we still do it? Not just because I made you, but because what was it from the beginning? Men's heights were already normally distributed. I didn't need the sample size to come in and save my ass. I took a sample of 1 and we did the problem because it was already normal. But this says if they don't tell me it's normal, if the sample size is greater than 30, I know it's normal enough. I can keep going. I can do that stuff. And the other thing it says is the new mean is the same as the old mean, and the new standard deviation gets smaller by this much. Those are the things it says. So let me give you this handout. Okay. Heat on earlier. I was like, that's good. Yes, it is. Don't worry, I'll put hers in there. Just makes it easy. Look at that there. Was somebody about to say something? Okay, if you need to borrow a calculator, you're up here. Might as well use a calculator.